Today's topics are relaxation times. There are two relaxation times, T1 and T2 relaxation times. We will see what these relaxation times are. Let's start the definition of monetization. The magnetic characteristics of a single proton cannot be observed. In fact, the collective magnetic property of protons in a particular location is measured in MRI. We previously calculated the relative numbers of protons at two energy levels. The conclusion was that around 0.35 ppm more protons aligned parallel to the field than those aligned antiparallel for about 1 Tesla of field and at room temperature. 0.35 ppm, this is very tiny difference. However, because there are 10 to the 22 protons in a unit volume of cubic centimeter, the difference in number of protons at two energy levels is significant. The net magnetic moment exists as a result of the substantial proton number difference between two energy levels as depicted schematically in the left figure. The precession frequency of protons in the same magnetic field is the same. So this magnetic nuclear spin process is the same Rameau frequency along the field direction. Their precession phases, on the other hand, are random. So the starting point of precession are different. So these are called phases. So phases are different. The precession frequency are the same, but phases of every nuclear spin are different. The monetization is defined as net magnetic moment of protons in a unit of volume, and it is denoted by vector m. In the figure, the longitudinal monetization along the field is represented by mg. The transverse monetization denoted by mxy, whose direction is in the xy plane, which is perpendicular to the field, becomes zero due to the random precession phases of the protons. So monetization components on the xy plane, which is called the transverse magnetic field monetization, is zero. So for example, for this nuclear spin, there are opposite side. There is the same, the different phases proton. So xy component of this magnetic moment cancelled out. So if we do the vector sum of the magnetic moment of nuclear spin, there is no transverse monetization there is only longitudinal modulation. In conclusion, protons in a magnetic field have net longitudinal modulation, but no transverse modulation. Let's look at what occurs to the longitudinal modulation when an RF pulse is applied along the x-axis. As the electromagnetic wave, the RF pulse contains both electric and magnetic fields. The heat effect is caused by the electric field, which does not alter the motion of the protons. So electric fields in the electromagnetic wave just give the heat effect, but the electric field does not change the motion of the modulation. On the other hand, the magnetic field, which is in y direction, this direction, SP1, provides torques to the protons and changes their motion. An RF pulse must have the same frequency as the Rameau precession frequency of omega equal gamma b in order to change their motion of the protons. We already mentioned the resonance condition. So this is actually a resonance condition. We have to supply the same energy of electromagnetic wave, which is the energy difference between two energy levels of nuclear spin. Protons receive the energy of the RF pulse and change their motion if the resonance condition is met. The motion of modulation vector mg, which is the collective vector sum of the magnetic moment of proton, can be used to characterize the effect of the RF pulse on protons. An RF pulse's magnetic field V1 in the y direction, V1, produces a torque mg cross B1. So the occasional motion for the modulation vector mg can be written as this. We already saw this occasional motion for mu. Magnetic moment mu is in the field of B, then that magnetic moment have a torque, and the occasional motion looked like this. We already saw this equation. Here, mu is mg and b is b1. The modulation vector mg rotates around the x-axis at an angular velocity of omega1 equal gamma b1 in the direction of the y-axis according to this equation. So according to this equation, modulation vector mg has torque due to b1. and rotates around the x-axis and move to the xy plane like this. And the angular velocity is given by omega1 equal gamma v1. The amplitude of the magnetic field v1 and time of duration t are used to describe a pulse. So we represent a certain pulse by v1 and t. If multiple pulses are used, the time interval between them must be specified, which is referred to repetition time of pulses and denoted by TR, time of repetition. So if we apply 2 pulses and the repetition time is TR. The modulation vector's rotation angle owing to an RF pulse is expressed as theta equal omega 1t, so theta equal gamma v1t. So the magnetic field amplitude and the duration time of an RF pulse are denoted by v1 and t in this equation. The radian is the angle unit. This angle unit is radian. The rotation angle of the magnetization vector is proportional to both magnetic field amplitude and the duration time of the RF pulse, according to this equation. Magnetization vector can be rotated at any angle to the y-axis direction because these 2 quantities, p1 and t, can be manipulated. 2 pulses, 90-degree pulse and 180-degree pulse are frequently used in MRI. A 90-degree pulse is used to convert longitudinal magnetization to transverse magnetization. So, by 90-degree pulse, longitudinal magnetization can be converted to transverse magnetization, so 90 degrees. On the other hand, 180-degree pulse reverses the longitudinal magnetization direction. So, magnetization to the field reverses antiparallel to the field. Okay, so we can choose B1 and T. Gamma is gyro-magnetic ratio of the hydrogen proton. So we can choose B1 and T to have this value pi over 2. Then we can construct the 90-degree pulse. The same thing here. You can use a little less B1 and a longer T, and this angle can be made to be angle pi. Now let's see the effect of 90-degree and 180-degree pulses on nuclear spins. in the static field of V0, nuclear spins precess around this V field, but the phases of nuclear spins are all different. So if we do the vector sum, there's only longitudinal marginalization survives, and transverse marginalization becomes 0, because x and y component of nuclear magnetic moment are all cancelled out. So there's only a longitudinal marginalization. Now, if we apply 90-degree pulse, then every nuclear magnetic moment rotate to the y-axis or xy plane. So every nuclear spin rotate 90 degrees. And these nuclear spins precess along the P field, and this also precess. So every nuclear spin precess around the P field. So they move together around P field. So we can call this phasing. And we do the vector sum of magnetic moment of nuclear spins. We can have this magnetization. So we have the transverse magnetization. So if we apply 90-degree pulse, then longitudinal magnetization convert to the transverse magnetization. On the other hand, if we apply 180-degree pulse, every single nuclear spin, the direction of precession reverses anti-parallel to the field. And if we do the vector sum, there's no transverse magnetization. There's only longitudinal magnetization, mg, but in this case, mg is anti-parallel to the field. So that means that this longitudinal magnetization reverses its direction by the 190-degree pulse. We already mentioned phasing. Every single nuclear spin precess around the V0 field, and these nuclear spins move together around the V field. So this is called the phasing. So they move together. So we call this, they are in phase or phasing. So nuclear spins parallel to the field flip to the XY plane by a 90-degree pulse to form the transverse margination. The spins rotate together in phase through the V field. Okay? So due to the 90-degree pulse, nuclear spins rotate 90 degrees and they are rotate together in phase through the V field. So we call this phasing. Now let's see the T1 and the T2 relaxation times. The net margination M0 along the magnetic field direction is the result of the vector sum of protons' magnetic moment. We already mentioned. This longitudinal margination vector flips to the y-axis and becomes a transverse margination vector when protons are given a 90-degree pulse. Okay? With a normal precession frequency, the transverse magnetization vector rotates in the plane. So this transverse magnetization vector rotates through the g-axis with a Rameau frequency. With a Rameau precession frequency, the transverse magnetization vector rotates in the plane. Okay. In a microscopic view, two things happen when a 90-degree pulse is switched off. Protons, actually proton magnetic moment vector, recover to their original orientation after being flipped by an RF pulse. Second, protons' RF pulse induced phasing is disappearing. Longitudinal magnetization is restored to its original value of M0 when the protons are flipped back to the original orientations. On the other hand, the transverse magnetization is disappearing. The loss of transverse magnetization is significantly faster than the recovery of longitudinal magnetization. The speed at which transverse magnetization disappears is determined by the dephasing process. Dephasing is also accelerated if there are any external magnetic inhomogeneities near protons. The inhomogeneity of the static magnetic field or other external magnetic sources present near the protons, such as MRI contrast agents, produces these external magnetization inhomogeneities. The T1 relaxation time is the time taken for longitudinal magnetization to recover. The spin lattice relaxation time is another name for this time. The energy of protons aligned antiparallel to the field is higher than that of proton aligned parallel to the field. As a result, antiparallel to the field protons flipping back to parallel to the field should release their extra energy and return to the lower energy level. The excess energy is released to surrounding atoms during interaction between protons and surrounding atoms, which emits a radio frequency wave. with the same frequency as the RF pulse provided to proton for the resonance. Because the spin-lattice interaction is important in the energy release process, the T1 relaxation time is also referred as spin-lattice relaxation time. The temperature of the surrounding atom is slightly increased during this interaction process, and so the T1 relaxation is also called as a thermal relaxation. So in T1 relaxation, nuclear spin along the field is moved up to the higher energy state by RF pulse. And this nuclear spin move back to the low energy state because RF pulse is turned off. So if we move this direction of nuclear spin, the energy is higher at this energy stage. The energy is lower in this stage. So if this nuclear spin want to move to low energy state, it should release the energy, and then this can be moved to the lower energy state. This means that the nuclear spin anti-parallel to the field convert to the nuclear proton parallel to the field. So in this process, energy should be released. So energy can be given to the surrounding lattice. So this relaxation is called the spin lattice relaxation. Spin means the nuclear spin, and the lattice means surrounding atoms. T2 relaxation time is also known as spin-spin relaxation time. Is influenced by the spin-spin interaction. The spin-spin interaction is one of the dipole-dipole interactions. Protons are magnetic dipoles. As a result of its interaction with nearby protons, each proton experiences a slightly different net magnetic field. As a result, each proton processes at a slightly different frequency, and thus phasing is eventually lost. Thus, the transverse magnetization is lost. The T2 relaxation is also influenced by the static magnetic field inhomogeneity or any external magnetic inhomogeneities. We already mentioned this behavior. The T2 relaxation time is referred as the T2 star relaxation time when both the spin-spin interaction and the external magnetic field inhomogeneities are taken into account. Figure below depicts the schematic dephasing of these three protons after RF pulse is turned off. The transverse magnetization rapidly decreases as the dephasing process progresses. We already said that here, also there are 3 nuclear spins. After 90-degree pulse is turned off, the interaction between neighboring spins, each spin has slightly different magnetic field. So they feel slightly different magnetic field, so the pulsation frequency of each nuclear spins become different, so phasing is lost. The T1 and T2 relaxation can be explained by the empirical vector equation, the Brock equation. Which is given by this equation, vector equation. Here M0 is longitudinal magnetization at the thermal equilibrium, and MXY is X component of magnetization and Y component of magnetization. If we take G-axis as the static magnetic field direction, we can decompose the magnetization vector into X and Y and G components as. So we can decompose the equation to these 3 different components equation. Here omega equal gamma B. Longitudinal relaxation is obtained by solving third differential equation, this equation. This is mg, right? So T1 relaxation is related to the mg. The solution of this differential equation is easily obtained by this. Here, longitudinal magnetization is 0 at t equals 0. So at this moment, the longitudinal magnetization becomes transverse magnetization at t equals 0. So mg becomes 0. So this term can be removed, and we have a G component of magnetization is changing as a function of time by this equation. And this equation can be plotted like this. If pulse is turned off, the nuclear spins anti-parallel to the field now move back to the original orientation. And finally, all nuclear spins back to the original orientation, then relaxation is complete. At this moment, the magnetization recovers to the original value, mg0, right? So if we wait for a long time, then all nuclear spin anti-parallel to the field move back to the parallel to the field, and so original magnetization can be obtained. So we have to wait for a long time. But T1 reaction time is defined as the time it takes for the longitudinal magnetization to recover up to 630% of its initial value. That means that this become 1, right? So 1 minus exponential minus 1, this will be 0.63. So 63%, right? So the T1 relaxation time is defined when the modulation recover 63% of its original value. The process of protons losing energy to surrounding lattice is related to T1 relaxation. I already mentioned this. This energy transfer is most efficient when the natural motional frequency of molecules surrounding protons is identical to the Raman precession frequency of protons. So if natural motional frequency of surrounding protons matches the Raman frequency of protons, then protons can easily give their energy to the surrounding atoms. Pure water molecule move very fast. It translate, rotate, and vibrate, so making it difficult for protons to transmit the energy to them. So water molecules bound to the hydrophilic macromolecules like protein, on the other hand, lose some of their mobility freedom in one direction. As a result, their natural motional frequency approaches that of protons, resulting in a more efficient energy transfer. So the protons inside the protein can give off their energy to the macromolecules of protein. So relaxation time becomes short. But protons in water molecule move very fast, so it's very hard for the protons to give off their energy to the water molecules. So protons in water have long T1 relaxation time. Because of rotational frequency of carbons and fat is close to the Raman precession frequency of protons, protons in fat have shorter T1 relaxation time. So protons in fat can easily give their energy to the protons in fat. The magnitude of the static magnetic field affects the T1 relaxation time as well. The T1 relaxation time increases as the magnitude of a static magnetic field increases. This is because the higher field, the higher the Raman precession frequency of protons, whereas the natural motional frequency of surrounding molecules does not change. So, in the high field, the protons has difficulty in giving off their energy to the surrounding molecules. Therefore, the T1 relaxation times in the high field is long. So we can see the T1 relaxation times in brain tissues. So white matter and gray matter, CSF. CSF is fluid and the fat. We already discussed the protons in the fluid have difficulty losing their energy to the surrounding molecules because water molecule moves very fast. So the protons in CSF has a long T1 relaxation time, and the protons in fat has a shorter T1 relaxation time. Okay? And in the high field, that's 1.0 Tesla and 1.5 Tesla. T1 relaxation time increases as field intensity increases. Okay? So you can see this behavior. So, in summary, tissues with a large water content have a longer T1 relaxation time. Now let's see the T2 relaxation time. This is a abbreviation. If we multiply I, that's complex number, to the second equation, this equation, and add it with the first equation. So we'll multiply I in second equation and add up to the first equation. We have this equation, and mxy is defined by this. The solution of this differential equation can be obtained as here. The term exponential I omega t indicates that the transverse margination rotates in the xy plane through the g-axis, which is direction of B field. This equation can be plotted like this, and mxy0 at equals 0, decaying very fast to the 0. You already discussed in the RF pulse field, the nuclear spins rotate together in phase through the B field. This is called phasing. But 90-degree pulse is turned off, then nuclear spins interact each other, and the field felt by each nuclear spin are different, so their precession frequencies are different. Consequently, the phasing is lost. So completely dephasing, then we get mxy will be 0. And T2 relaxation time is also defined as the time it takes for the transverse normalization to decay 60-30% of its original value, which means that this term become 1. So that means exponential minus 1, that is 0.37, right? So 63, this is 63%, right? Percent is lost. At that time is called T2 relaxation time. T2 relaxation is influenced by the strength of the spin-spin interaction between protons and surrounding molecules. Protons in tissues with the largest spin-spin interaction between neighboring protons and the tissue molecules have a faster T2 relaxation time as a result of this. So the interaction between the spins and the spin and the neighboring atoms is strong, then we have a short T2 relaxation time. The distance between hydrogen proton is in pure water is relatively large. Thus, one proton's interaction with another is relatively small because they are distant away. So as a result, protons in pure water have a long T2 relaxation time. Human tissues, on the other hand, have more dense structure, which means that the protons interact more. There are more neighboring atoms and more neighboring nuclear spins. So the interaction becomes strong. Therefore, we have a short T2 relaxation time in dense structure. Dephasing occurs more quickly due to the numerous spin-spin interactions. As a result, the T2 relaxation time in dense tissue is shorter than in less dense tissue. You can see this in the brain tissue. CSF is fluid, and fat is more dense tissue, right? So, in the dense tissue, the protons have shorter T2 relaxation time. But in fluid or in water, the protons have a long T2 relaxation time. Okay, we can see this behavior in the brain tissue. Summary: tissues with a large water content have a long T2 relaxation time. We can see this behavior in the brain tissues. I can omit this one. And normally, the protons in tumor have longer relaxation times than protons in normal tissue. Okay, so tumor tissue has longer T1 relaxation time than that of normal tissue. We can see other organs, tumor tissue has longer T1 relaxation time. Okay. T2 relaxation time, let's see, slightly different. Okay. And this is normal tissue and tumor tissue. So the protons in tumor tissue has a longer T2 relaxation time than those in the normal tissue. We have the same behavior in the T1 and T2 relaxation times. In the liver, you can see also tumor tissue has longer T1 and the T2 relaxation times. Okay, in kidney, tumor tissue and normal tissue. Okay, so you can see the same behavior. In muscle, you can see the same behavior. Okay. Now let's see some example regarding to the topics you already mentioned. A radio frequency pulse has a magnetic intensity of 3 millitesla. For a 90-degree pulse, how long should RF pulse's duration time must be set? We can use this relation, and gamma is known and B is 30 millitesla, and theta we want 90-degree pulse, so pi over 2. So we can get pulse duration time 1.96 microsecond. Next example. A certain tissue has T1 and T2 relaxation times of 1000 and 200 milliseconds respectively. A 90-degree pulse changes all longitudinal modulation to transverse modulation. Okay. What percentage of the transverse modulation disappears at 500 milliseconds after 90-degree pulse is removed? And at the same time, what percentage of longitudinal modulation recovers to its original value? The recovery of modulation, longitudinal modulation is represented by this equation. So we know T1 is 1000 milliseconds, and T we are observing the recovering of modulation 500 milliseconds, so we can have this number. So 39% of longitudinal modulation recovers. And see the transverse modulation, decay of the transverse modulation is represented by this equation, and we put the T2 to 200 milliseconds, and the observation time is 500 milliseconds, so you can get this one. Okay, so this is the remaining one, right? Remaining transverse modulation. So the question is the percentage of the longitudinal modulation. I mean here, percentage of transverse modulation disappears, right? So at this time, 500 milliseconds, 92% of original transverse modulation disappears. Okay. Next example. Due to the inhomogeneity of the static field and spin-spin interaction between nuclear spins, the local magnetic field Vx, Vy, and Vz are generated at the specific location. The T1 and T2 relaxation times are affected by these fields, V1, Vx, Vy, Vg fields. Use the Bragg equation to explain why the T1 relaxation times is always longer than the T2 relaxation time. So Bragg equation is this one. This is local fields generated. We can decompose this equation into three XYZ components. Here mg is related to the T1 relaxation time, and mx and my are related to the T2 relaxation time. Okay. So let's first this equation. The local field Vz has no effect on the longitudinal modulation mg. Okay. There is no Vz here. We cannot see Vz in this equation. On the other hand, transverse components mx and my are dependent on all local field components Vx, Vy, and Vz. You can see Vy, Vz, and also Vx and Vz. So in the equation of mg, there is no components of Vz, but in the equation of mx and my, we have all local components, Vx and Vy, Vz. So the recovery of mg is related to T1 relaxation time. On the other hand, the decay of both mx and my is related to the T2 relaxation time. Since mg is less affected by the local magnetic field than mx and my, the T1 relaxation time is always longer than the T2 relaxation time. So mg is not affected by local field Vz. However, mx and my are affected by all local components. So mg T1 reaction time is always longer than T2 reaction times. We want to omit these examples. You want to also omit these examples.